All right, in 10.1c, we're going to talk about inference for experiments. How does it change our process when we are dealing with an experiment versus a sample? So what mistakes do students often make when they define parameters in experiments? How do you avoid it? So this is probably the biggest difference when you're dealing with an experiment in how you define your parameters and your wording. It's going to feel a little bit like English class, but hey, work with me. So it's better to use present tense or future tense when you define the parameter. Don't use language that refers to the sample, like the proportion of people who took this drug, da la la. That's like past tense, and it's speaking just to the sample of people. But remember, we define parameters, we're talking in terms of the bigger population. So I would, instead of saying that, I would use the proportion of people like these who would take this medication and respond in this way. So it's very generalized. It has to be generalized to the population, and don't refer to volunteers of an experiment or subjects, or in any way use past tense, use future tense, or use people like these. Okay, so I'm going to walk you through a 4-step process with an experiment so you can kind of see what the differences look like. In an effort to reduce healthcare costs, General Motors sponsored a study to help employees quit smoking. In the study, half the subjects were randomly assigned to receive up to $750 for quitting smoking for a year, while the other half were simply encouraged to use traditional methods to stop smoking. None of the 878 volunteers knew that there was a financial incentive when they signed up. At the end of 1 year, 15% of those in the financial reward group had quit smoking, while only 5% in the traditional group had quit smoking. Do the results of the study give convincing evidence that a financial incentive helps people quit smoking compared to a traditional method? All right, so when I start my state step, I have to be aware that this is an experiment, right? There are two different treatments going on, one using traditional methods and one using an incentive method. So 878 volunteers split into two groups. They're both encouraged to quit smoking, but at the end, half of them get an incentive, the other half don't. Now, let's move on. Okay, so the state step. We want to test, is the difference in proportions of those two groups equal to 0, meaning no difference? Or is the incentive group, P1, minus the no incentive group, going to have a bigger percent be successful? So that would be a greater than 0. At the alpha equals 0.05 level, where, let's define this, P1 is the true quitting rate for employees like these who, with the incentive, so notice I use like who had the, I can't say who had an incentive, but like these with an incentive. And then P2 is the true quitting rate for employees like these without an incentive. So rate is another word we can use for proportions, by the way, so don't let that mess you up. All right, on the plan step, we name our tests. We're going to do a 2 proportion Z test if the conditions are met. And I've pulled my values out of the question. So the proportion of P1, those are the ones with the incentive, they had a 15% quit smoking out of the 439. That 439 is half of 878, by the way. So the sample sizes were the same. But then in group 2, the one without the incentive only had 5% quit smoking. So there's my 2 percentages and my sample sizes. So check for random. Let's see. Were the treatments randomly assigned? Okay. It does say it right here. They're randomly assigned. They're not samples, but they're randomly assigned to groups. That's where we're different with an experiment. So they are randomly assigned. Now, the 10% condition, because we're not sampling, we don't need to check for a 10% condition issue. The 10% condition is not necessary for this because we're not dealing with samples. Bottom line, we're dealing with a group of volunteers. And then, for the large counts test, we need to figure out our pooled version of the p-value, right? So here's another way to look at it. Sample size 1 times p hat 1, sample size 2 times p hat 2, divided by the sum of the samples, right? So as I plug in my numbers, it looks like this. Here's my first sample size in proportion, second sample size proportion. I'm going to find those values first, add them up, then divide by the total. That gives me a pooled p hat value of 10%. Now that's the value I'm going to use when I check large counts. So there it is. I check it for both samples. They happen to be the same size, so it's the same. But both are greater than or equal to 10, so my large counts test is satisfied. Okay, I have to show all this work. Yes, you do. Calculator won't do that for you. All right, for the do step, all right, you're going to use your calculator for sure. Two proportion z-test. When you get to that test, this is what the screen's going to look like. I'm going to walk you through where did these numbers come from. Well, it comes from where we calculated the pooled p-value. Right, here's what we did on the previous screen. X is the number we get when we multiply these two together. Now, we can't put it in like this with a decimal. We have to round it to a whole number. So round it to 66. N1 is my sample size. X2 is this number rounded to a whole number. So I rounded to 22, and my sample size was 439. And then notice I need to pick the correct inequality. In this case, it was a greater than. That's what I used in my alternative hypothesis. And then I'll hit calculate. And this is what my output will look like. There's quite a bit going on here. Notice I have my p-hat values calculated for me. My pooled p-value is in there for me. But sometimes you need these values to get there. So you may have to do it by hand. Now, what you really need to draw out of this is the z-score and the p-value. All right, so my z-score, easy enough, is 4.95. Now, the p-value, do not tell me the p-value is 3.82. It's not. Remember, it's a probability. It can't be greater than 1. Notice the e to the negative 7. That means that's really 6 zeros in front of that 3. Okay? So it's approximately 0. So when you see this, just say that the p-value is approximately 0, because it is. Now moving on to conclude. So since the p-value is approximately 0, and that's less than alpha, or 0.05, we reject the null hypothesis. There is convincing evidence that financial incentives help employees like these quit smoking.